This production is brought to you by the University of Edinburgh.
Thank you all for being here. So I'm going to talk about unifying logical and statistical AI. This is joint work with all the people here. I will start with a little bit of motivation. Oopsie, wrong button. I will start with oops. This is a new pointer that I just got because the other one died, so forgive the glitches. So motivation and background, and then I will describe Markov logic, which is sort of like the heart of this talk. I will say a little bit about how to do efficient inference in Markov logic and how to do learning. A little bit about some software implementations of this that are available, and talk about applications, some of the applications that people have done so far, and conclude with a little bit of discussion. So here's one possible way to motivate this talk. Back, at the Dartmouth conference when people studied AI, they were, sort of like shooting to have, reached human level AI by now. But if you compare the IQ of people, right, with the IQ of machines, and you extrapolate the trend, right, even a century after the original Dartmouth conference, we're not going to be anywhere near human AI. Okay? And the question is, what can we do about it, right? We could just give up on it, but that seems like a cowardly thing to do. Well, I would argue that what we want to try to do is increase our rate of progress. Not just make more incremental improvements of the kind that we do every day, but try to come up with things that will make all those increments bigger, such that we can progress towards our goal at a higher speed. And if we can come up with enough of these, I think it maybe becomes possible that AI will be reached within at least the lifetime of some of the people here. Okay? So what I'm going to talk about today is one possible candidate for producing one of these, increases in the slope of progress. And that has to do with what you might call the great AI schism, which has riven the field since its very beginnings, which is the chasm that exists between the logical approaches on the one hand and the statistical approaches on the other. Okay? Pretty much in every subfield of AI, there's a logical approach or set of approaches and the statistical approach. Like, for example, in knowledge representation, on the logical side you have things like first-order logic and all its variants. On the statistical side you have things like Bayesian networks, Markov networks, and so forth. In automated reasoning you have things like satisfiability testing and theorem proving. Here you have things like MCMC, belief propagation. In machine learning, on the logical side, you have inductive logic programming, rule induction, things like that. On the statistical side, you have things like neural networks and EM and so forth. And the same thing extends to planning, for example, classical planning versus MDPs, natural language processing, definite clause grammars versus probabilistic context-free grammars, and so forth. Right? And if you go to AI conferences, you will often hear the people who work on one side of this divide complaining about the limitations of the other. Right? And the interesting thing is that they're actually both right. They're both right because neither logical approaches by themselves nor statistical approaches by themselves are enough for the kinds of problems that we need to solve in AI. And what we really need to do is to unify the two. Right? The real world that our intelligent agents are going to have to work in is both very complex and full of uncertainty. Logic is good for handling the complexity, and probability is good for handling the uncertainty, but what we need is both. In one language, one system. And that's the goal. We're, of course, not the first ones to work on this. There's been, things going back at least to Nielsen in AI and his probabilistic logic, the theoretical stuff that Joe Halpern and others did, knowledge-based model construction in the early 90s. More recently, this field has grown up of statistical relational learning, where the goal is to combine statistical learning and relational learning. And a whole bunch of representations have been proposed there, including things like stochastic logic programs, probabilistic relational models, relational Markov networks, and many others. The ones I'm mentioning here are just the most direct predecessors to what I'm going to talk about here, which is Markov logic. And Markov logic, compared to previous approaches, has a number of advantages. One is that it's more general, in that it's really fully first-order logic and full, probabilistic modeling. It's also simpler. Interestingly, in many ways, it's a much simpler language than many of the things that have come before. And it comes with a complete set of learning and inference algorithms that are available in open source software. You can use them tomorrow. For previous approaches, in many cases, there are no algorithms, for example, for learning. And when there are algorithms, often they're not really available and so forth. So if you want to do this in practice today, Markov logic is probably one of your best options. So here's a one-slide summary of what I'm going to talk about. So the syntax of Markov logic is very simple. It's just first-order logic with weights on the formulas. The semantics is that I'm going to treat those formulas as templates for features of Markov networks. So a set of formulas with weights is basically going to tell you how to build a probabilistic model. And then we're going to see various inference algorithms. In particular, the one I will focus on here is the most recent one called lifted belief propagation, which combines belief propagation with ideas from theorem proving, namely, the whole idea of lifted inference. And then the learning algorithms, not surprisingly, are going to combine ideas from statistical learning like voted perceptrons and pseudo-likelihood with inductive logic programming. And the software that we have implementing this is called Alchemy. This has been applied. Markov logic is actually only a few years old, but it's really taken off, and people have applied it to a lot of things by now. The application that I will use here to illustrate what you can do with Markov logic is information extraction, but it's been applied more broadly in a lot of natural language problems, social networks, computational biology, robot mapping, etc., etc. And the list continues to grow. So let me just start with a little bit of background to make sure we're all on the same page. So first of all, what are Markov networks? So we're going to combine Markov networks with first-order logic, so let's start by seeing what Markov networks are. So a Markov network, like a Bayesian network, is a model of the joint distribution of a set of variables. And it's a graphical model, so we have a node for each variable, and now we have an undirected edge between two nodes if there is a direct dependency between them. And the independent semantics of this is that a node, for example, here, if I take out cancer and asthma, cough becomes independent of smoking. Okay? So graph separation in this graph tells you what variables are independent of what variables given others. Okay? So the graph gives you the independent structure. Now the parameters are given by what are called potential functions. And there's a potential function defined over each clique of the graph, right? Each completely connected subgraph. So for example, and the potential functions can take on any non-negative real values. So for example, here's the clique, smoking and cancer, assuming the variables are Boolean, there are 4 states, and here's the value of the potential function for each one of them. Okay? And the main thing that this potential function is capturing is the fact that the state smoking and not cancer is less likely than the others, and the reason for that, of course, is that smoking causes cancer. Okay? And now the probability of a state of the world is just the product of all the potential functions normalized. Okay? Now, there's a problem with this, is that if the cliques are large, then this becomes intractable, right? Because the size of a potential function is exponential in the number of variables in the clique, right? So what can we do about that? Well, we can use what's called a log linear form for the model, something that's very popular with statisticians. And the idea is that instead of a product of factors, what we're going to have is an exponentiate sum of weighted features. Okay? And you can always convert from one to the other by defining a feature for every state of the clique and letting the weight be the log of the potential. Okay? The thing that you gain, though, is that I could have a very large clique with a gazillion states. If I know what the important few features of that clique are, I can just write what those features are and their weights, and now I still have a compact model. So for example, if I define the following feature, that's 1 if you don't smoke or have cancer and 0 otherwise, and give it a weight of 0.51, this implements the same Markov network as we had here. Okay? And of course, in this case, the savings is not very impressive, but if you had a large clique, the savings would be huge. Okay? So let me just say a little bit about first-order logic, just to get some terminology down. So formulas in first-order logic are made up of logical connectives like conjunction, disjunction, quantifiers, etc., and 4 types of symbols. Constants representing objects in the domain, say Anna, variables like x, functions like mother of x, and predicates that represent properties of objects and relations between objects, like, for example, friends x, y. And I'm going to call a grounding of a predicate or a formula the result of replacing all of its variables by constants. So for example, if friends is one of the predicates in my domain and Anna and Bob are 2 of the constants, one possible ground atom is friends and a Bob. And this is just the Boolean variable that's true if Anna and Bob are friends and false otherwise. Okay? And I'm going to call a world, also known as possible world, model, interpretation, Herbert interpretation, state, and a bunch of other things, an assignment of truth values to all the ground predicates. Okay? So I have my language of predicates and constants. I combine them in all possible ways. I get a very large number of Boolean variables, and by assigning truth values to them, I have completely described the state of the world. Okay? And the main thing that we're going to be dealing with in this talk is probability distributions over possible worlds. Okay? All right, so now let's get to the heart of things, Markov logic. Here's an intuitive way to introduce Markov logic. A logical knowledge base can be seen as a set of hard constraints on possible worlds. Meaning if you violate even one constraint, if you violate a single grounding of a single formula, the world becomes impossible. Okay? And this is why logic is so brittle. Logic does not make a distinction between a world that violates one formula and the world that violates all of them. So as soon as you violate even one little thing, you fall off a cliff, right? What we would like to have is a more smooth degradation as the world violates more of your formulas. So how about we make the formulas soft constraints instead of making them hard constraints? Okay? So now what happens is that when a world violates a formula, it doesn't become impossible, it just becomes less probable. And we're going to give each formula a weight that represents how strong of a constraint it is. So if I really believe in a formula, you give it a high weight, and you pay a big penalty for violating it. Okay? And now the probability of a world is going to be a log linear model of the form that we just saw, where the formulas, the groundings of the first order formulas are the features. Okay? And so we get this behavior that the more formulas you satisfy and the higher their weight, the more probable the world is. Okay? So this is the intuition. Here's a more precise definition. I'm going to call a Markov logic network, or MLN for short, a set of pairs FW, where F is a formula in standard first order logic, and W is a real number, positive or negative. That's the syntax. The semantics is as follows. Together with a set of constants that could just be the constants that appear in the MLN or some others that you define, the MLN is going to define a Markov network as follows. The Markov network is going to have one node for each grounding of each predicate in the MLN, and it's going to have one feature for each grounding of each formula in the MLN with the corresponding weight. Okay? So all the features that are groundings of the same formula are going to have the same weight. Here's an example that will hopefully make things clearer. This is a picture from the New York Times a few months ago. It's about a social network and who smokes and who doesn't. So if you want to combat smoking, what do? Turns out that a very important factor in who smokes and who's not is whether your acquaintances and your friends smoke. So what this shows is smokers, this was a study that was done. This is 1,000 smokers in 1971 and in 2000. And the nice thing is that many fewer people smoke now, right? The circles are smaller and there are fewer. But the other thing that's noticeable here is that people don't stop smoking at random. They stop smoking in clumps. If your friends stop smoking, that makes you more likely to stop smoking. And if they don't stop, you'll have a hard time stopping as well. Okay? So let's try to model this domain. Let's start by doing it in English. So we have two statements. The first one is smoking causes cancer. And the second one is friends have similar smoking habits. Okay? And anybody who knows AI 101 knows how to turn this into logic. You write for every X, smokes X implies cancer X, and for every XY, friends XY implies that smokes X and smokes Y are equivalent. Okay? Very easy. There's only one problem, which is that these two statements were true, and these two are false. Right? They're false because not everyone who smokes gets cancer, and certainly not every pair of friends has the same smoking habits. Okay? But if we turn this into an MLN by giving weights to the formulas, now we're back to what we want. We have statements about statistical regularities about the world. Most smokers get cancer, etc. And this formula here has a higher weight than this one because it's a stronger regularity. Right? Intuitively, stronger weights correspond to stronger regularities. Okay? So now we have this MLN. What is this actually saying about the world? Well, let's suppose that we have a very simple world with only two people in it, on a desert island or something, because that's what fits on a slide. And let's call them Anna and Bob. Not very original, but usually it's Alice and Bob. So we're using Anna and Bob here because Anna is even shorter than Alice. But, to be even shorter, we're just going to, represent them by A and B. So the rule now is that we're going to have a node in the network for every grounding of every predicate. Okay? So we're going to have cancer Anna, smokes Anna, same thing for Bob. And then we're going to have friends Anna, Bob, right? Friends Bob, Anna. Notice friendship is not symmetric. Sociologists will tell you that, right? Bob could be a much better friend of Anna than she is of Bob, right? And this happens in practice, right? And then there's like friends Anna, and friends Bob, Bob, which maybe have to do with their self-esteem or something, right? So it's like a degenerate case of friendship, right? So these are the nodes, right? And at this point, what I have is a bunch of Boolean variables. I can now forget where they came from in some sense. Another question is like, what is my distribution over these Boolean variables? Well, the rule was that I'm going to have a feature, right, for every grounding of every formula. And wherever I have a feature, I'm going to have to connect the corresponding nodes in a clique, right? So for example, smokes X implies cancer X is going to create the feature smokes Anna implies cancer Anna, and therefore there's going to be an edge here. And same thing for Bob. Right? So this was a two-way clique, so I have, only one line here. This here has three literals in it, so it's a three-way clique, so I'm going to create triangles, right? So I'm going to have a triangle now between smokes Anna, friends Anna, Bob, smokes Bob, etc. Okay? So now this is my complete graph of the Markov network, right? And now the full distribution that this represents is here. Right? So it's going to be the normalized exponentiated sum over all the formulas of the weight of the formula times the number of true groundings. Okay? So now the more people that smoke, the more smokers that have cancer, the more probable the world becomes. And if there's only one smoker that doesn't have cancer, that makes the world slightly less likely, but not impossible. Okay? Another important thing to notice is that an MLN does not actually represent a single distribution. This is one of the things that makes it powerful, is it actually represents a whole family of ground distributions depending on the domain that you apply it to. In particular, if you apply it to a large domain, to a domain with a lot of constants, you'll have a very large Markov network. Otherwise, you'll have a small one. But what they have in common is that they're all repetitions of the same templates. Okay? Another important point is that this looks very nice at this point, but it doesn't look remotely practical, right? I'm going to have an exponential number of nodes, and I'm not even going to get off the ground, right? So what do? Well, this is where actually a lot of the progress has been, and we're going to see some of it shortly. But the first thing that you can do that's very simple and already very useful is to have typed variables and constants, okay? And you only replace things by the corresponding types, and this already really cuts down on the size of your network, okay? Now, in Markov logic, we can handle the full range of constructs of first-order logic, including functions, existential quantifiers, infinite domains, continuous domains. I'm not going to talk about that here for the sake of brevity, but if you're interested, I can certainly point you to the papers, and you can read more about it. So how does this relate to the kinds of statistical models that people use in AI and machine learning today? Well, the nice thing is that pretty much all of them fall out as very simple special cases of Markov logic. And again, we'll see examples later. Pick your own favorite method, conditional random fields or Bayesian networks or maximum entropy models, etc., etc. All of these can be straightforwardly expressed in Markov logic. In addition, Markov logic gives you something very important, which is the ability to deal easily with non-IID data. So IID means that all your objects are assumed to be independent and to come from the same distribution. And this assumption is almost always made in statistical learning because it makes life easy, but it's false. Like, for example, my properties don't just depend on me, they depend on the properties of people that I'm related to. Like, you might influence me to start smoking and so forth. Okay? In Markov logic, this is easy to handle in the way that we just saw. You introduce, predicates that represent relations, and then, you have dependencies that are mediated by those. And Markov logic also makes it very easy to compose these models simply by having them share predicates, right? So I write the formula that represents a CRF, and the formula that represents, or a set of formulas that represents, say, a logistic regression, and now I can compose the two simply by virtue of sharing predicates and do joint inference over all of them. Okay? What about the relation to first-order logic? Well, it should be fairly intuitive that first-order logic is the limit of Markov logic that you get when you let your weights go to infinity. Right? Because then your soft constraints become hard constraints. And indeed, there's a theorem that says that every entailment query in logic can be answered by computing conditional probabilities on an MLN that you get by taking the logical knowledge base and giving infinite weight to all the formulas. Okay? Of course, we're really interested in the case where the weights are not infinite, and there we can still say something interesting, which is the following. If your knowledge base is satisfiable, meaning it's possible to make all the formulas true at the same time, and all the weights are positive, which you can always ensure by flipping, by negating formulas with negative weights and flipping the weights, then the satisfying assignments are the modes of the distribution. Which means that even in the finite case, the worlds that first-order logic are still there. They're the modes, they're the peaks of the distribution. The difference is that now, when you move away from the peak, you don't fall off a cliff, but your probability just gradually goes down. Most importantly, in first-order logic, if you have a contradiction, either direct or indirect between your formulas, all hell breaks loose, right? At that point, everything follows and things break down. Which means that you can't really build large knowledge bases because it becomes impossible to build a large knowledge base without making sure there's no contradiction. And you can't combine knowledge bases from multiple people as on the semantic web because they'll be full of contradictions. With Markov logic, however, contradictions between formulas are not a problem. Because what Markov logic does is it's going to weigh the evidence on both sides and it will output a probability for your proposition. Okay? So we can potentially do a lot of things with Markov logic. Of course, this will all be only a theoretical exercise unless we can come up with efficient inference algorithms. Yeah?
If you have a contradiction, everything becomes satisfiable. So does that mean everything is a vote?
No, so the way we handle this, right, we're going to see shortly how we handle this, but the way we do inference with a satisfiability solver is that we do weighted satisfiability. And if you have hard constraints, you're still in the logical situation, and, basically a contradiction will make things break down. But if you have a contradiction between formulas with a finite weight, right, what happens is that we're just going to look for the possible world that maximizes the weight, because that's the most likely world. So if those two contradictions, if one of them has higher weight, we will prefer that one. We can also just compute the probability by, basically computing the conditional probability of that statement given even the contradictory ones.
I'm just trying to relate it to your previous statement about mode, because I can't see.
Everything becomes provable, not everything becomes satisfiable.
No, so I see your question. So this statement was supposing the knowledge base is satisfiable. Right? If the knowledge base is not satisfiable, you may still have modes, right? But those modes will not be the words that first order logic likes anymore. Okay. So at that point, that correspondence breaks down. Okay. Okay, so inference. How can we do efficient inference in this language? Things don't look very promising, right? Because inference in first order logic is not exactly efficient. In fact, it's undecidable. And inference in probabilistic models is also not efficient. It's sharp P complete, right? So, we're combining sharp P with undecidable, and, that things aren't looking good, right? So, surprisingly, though, we've actually been able to get very far, we and others. And what I'll show you here is one example of how and why. So there's two main kinds of inference that people usually want to do. One is what it's called MAP or MP inference, which is finding the most likely state of the world given your evidence. Okay? This, for example, what Viterbi does in hidden Markov models, for those of you familiar with it. And we've developed a number of algorithms for this that I will not go into here. They're based on weighted satisfiability testing, as I just mentioned. The other type of inference that you often want to do is to just compute marginal and conditional probabilities, right? What is the probability that, Anna gets cancer given that Bob smokes and, he's her friend, right? For this, we can use things like Markov chain Monte Carlo. And again, we've developed some efficient algorithms, including something called MCSAT, which combines MCMC with satisfiability testing. There's also this old idea, which we've generalized, called knowledge-based model construction, where you don't actually ground out the entire network. You only ground out the minimum network that is needed to answer your query, right? And this, can itself save you a lot. The most recent method, and the one that I will cover here, though, is something called lifted belief propagation. And the idea here is that we want to do lifted inference in the same way that we can do lifted inference in logic, except that we want to do this in this new, more general probabilistic setting. So what's the idea here? The thing that's so great about inference in first-order logic is that I could actually do inference for a whole set of objects at once, irrespective of the size of the set. In fact, I could even do it for an infinite number of objects in finite time, right? And in the past, this has not been possible in probabilistic models. Right, what people do in these types of models is they create the ground network very large and then do inference on it, which might not be possible, or even if it is possible, might be very slow. What we like to be able to do is lifted probabilistic inference. And the way we're going to do that here is we're going to group the atoms and the clauses in the network into indistinguishable sets. And by indistinguishable, I mean, think of belief propagation, which I will review shortly. Belief propagation works by atoms sending messages to each other and to features, or to each other via features, right? If two atoms send and receive exactly the same messages throughout belief propagation, it's actually a waste of time to do this computation twice. I can just do this once for both of them. And if there's a million of them, then my computation, is a million times smaller. So this is exactly what we're going to do here. let me just mention that prior to our work, the only thing that people had developed was a lifted version of variable elimination, which was certainly an important advance. The problem, of course, with variable elimination is that it's an exact inference method and it blows up and it doesn't scale to real-world problems. All the things that we tried to apply lifted variable elimination to, we weren't even able to finish because it ran out of memory. So, how can we do lifted belief propagation? Well, here's the basic idea. So, for purposes of belief propagation, it's useful to think of your network as what's called a factor graph. A factor graph is a bipartite graph with two types of nodes. Some nodes are your variables, in our case our ground atoms, and the other nodes are your features. Okay? And each node is connected to the features that it appears in, and vice versa. Okay? And now the way belief propagation works is that in essence, we start out with each node having a crude approximation of its marginal, let's say a uniform distribution. And then the nodes send messages to the features, and the features send messages back to the nodes. And basically, the message that a feature sends to a node is what it thinks the node's marginal distribution should be. Right? So the nodes update the features with a new marginal, and then the feature computes what it thinks the marginal should be. And basically the way the node computes its new marginal is by multiplying the marginals of all the features, its marginals according to all the features that it's in. And the way a feature computes a new marginal for the node is by summing out the other nodes from the feature. Right? So I have here, e to the wf of the feature, and what I'm doing now, and this is why this is an approximation, is I'm pretending that the other nodes are independent. So I take their marginals, I multiply them, I multiply it by the factor, I sum it out, and what I have is a marginal on this guy. So the node receives the marginals from the features, multiplies them, that's its new hypothesized marginal, and this keeps going until things converge. Okay? Belief propagation, this has received a lot of attention in recent years. It's still a very active area of research how to do this better. The problem that we're going to deal with here now is that typically people do this in networks with tens or maybe hundreds of nodes, and we're looking at networks with millions or billions of nodes and features, right? So we need to do something different. And the way what we're going to do is we're going to notice that often, some sets of nodes send exactly the same messages to their features and vice versa. So if I can somehow identify these, let's call them super nodes and super features, then instead of sending all these messages back and forth, I can just send these. Right? I send a message from this super node to the super feature, which replaces all the different messages that each node would have to send to each feature. Okay? And as it turns out, now I can do belief propagation on this lifted network in pretty much the same way as before, except that now the messages are being lifted to certain powers because they represent the product of a lot of messages. Okay? So this is the basic idea. So here's how the algorithm works. First of all, I'm going to form my lifted network, and then I'm going to run belief propagation on that lifted network. Okay? And the lifted network is composed of these super nodes and super features, and a super node is all the nodes that send and receive exactly the same messages, and same thing for super features. Okay? And now we can guarantee that when you run belief propagation on this network, that hopefully will be much, much, much smaller, you get the exact same results as if you're running this on the full ground network. Okay? And of course, the time and memory savings can be, orders of magnitude. So the crucial question is, how do you form the lifted network? Right? That's the hard problem. So here's how. Let me just give you a rough idea of how you do that. Initially, we have some evidence, meaning some known truth values for some predicates. So we can divide each predicate into 3 supernodes. One contains all of its true groundings, one contains all the false groundings, and one contains all the unknown groundings. And of course, you don't necessarily have all 3 of them, but in the most general case, you do. Okay? And now the first thing that we're going to do is form superfeatures from the supernodes. And the superfeature is in essence a join of the supernodes that appear in it. Right? If I have RXY and SYZ, right, then I have a feature that's the conjunction of the two. The feature is over X, Y, and Z joined on Y. Okay? So the superfeatures are going to be joins of the supernodes. Right? And so I'm going to form them by, if each supernode could be true, false, or unknown, then for the superfeatures there's going to be, suppose there's 2, right? There's going to be true, 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 false, true, unknown, right? So I have these combinations, right? So in this way, I can create a generation of superfeatures from my initial supernodes. Okay? Now the next step is that I think of this as having started at the evidence. Now the evidence induces a finer subdivision of the features into superfeatures, but now these in turn can cause other nodes that they were connected in to become subdivided, right? So how do we do that? Well, it's by projecting the superfeatures down to the predicates, right? So say I have a feature over x, y, z, including a predicate rxy, right? I project this onto rxy by getting rid of z and adding up the results, right? This is the key. So what happens is that my new supernode is going to be all the groundings of the predicate that receive the same number of projections from the features, right? Because if two atoms receive exactly the same number of projections from the same features, then they're going to receive the same messages, right? And therefore they can be treated as a supernode. So now I have a new generation of supernodes, and from that I can induce a new generation of superfeatures, and I keep on doing this until it converges, okay? And we have a theorem that says there exists a unique minimal lifted network, minimal in having the minimum number of nodes and features. And this algorithm finds it, and BP on the lifted network gives the same results as on the ground network. Okay? There's still an important remaining issue, which is how do we represent the supernodes and superfeatures during the network construction, right? Once I've constructed the network, this just looks like a regular network, and I can run belief propagation in it, and it's guaranteed to never be slower than running on the full network. And in fact, it could be way faster, right? But during network construction, I need to somehow represent my nodes and features. Now, the easiest way to do that is to represent them by, database tables, right? Lists of tuples, the list of the true ground atoms, and so forth. The problem is that if you do that way, then that can become the bottleneck, right? Because those tables could become very large. So the next option is to use a more resolution-like approach where you use equality. We say, well, these are all the atoms except the ones where x is equal to a. Okay? Or only the atoms where x is equal to a and y and z are free to vary. Okay? And this is already going to be more efficient. What we can do that's even better, and that we've been working on recently, it's not published yet, is we can actually form clusters of nodes and clusters of features, right? And now this can be much more compact than even the resolution-like representation. And we can also imagine doing that approximately and getting even more gains, which we have. So let me actually skip over this part. These are some interesting open questions that still remain here, but in the interest of time, let's keep going. We can come back to this if people are interested. And let's talk a little bit about the learning. Okay? So at this point, we actually have inference algorithms that are good enough to do real applications in reasonable time. And I will mention some later. But what about learning, right? Where do these weights and these formulas come from? We would like to learn them from data. So the data now is a relational database, not just one table as in traditional machine learning, but it's going to be a database with multiple relations. Here I'm going to make the closed world assumption, which is that every atom that is not in the database is assumed false. And that makes things easier. If you don't want to make that assumption, then those atoms are unknown, and you will need EM versions of these algorithms, and they are available in this Alchemy software that I mentioned, but I'm not going to go into them here. So now there's two tasks, learning parameters, in our case the weights, and learning structure, in our case the formulas, and they can be done generatively and discriminatively, so let's briefly look at each of these. So first of all, let's look at generative weight learning, right? The first thing that you want to do. So what we do here is we want to, the standard approach is maximize likelihood, so we want to find the weights that make the database that you're seeing maximally probable, right? And unfortunately, you can't find them in closed form, but fortunately, the likelihood as a function of the weights is a concave function, which means it has a single global optimum, and we don't have to worry about initialization and getting trapped in local optima and all of that. And in fact, the gradient, so now we can do this by gradient descent, right, using fast second-order techniques like LBFGS or conjugate gradient, which again are available in Alchemy. And the gradient actually has a very intuitive form. And it's as follows. The derivative of the likelihood with respect to a weight is just the difference between the number of true groundings of the corresponding clause in the data and the number that's predicted by the MLN. Okay? So if the MLN predicts that a formula is true less often than it really is, its weight needs to go up. And if it predicts more often, then it needs to go down. And once all the predictions and the empirical counts line up, we've reached the maximum likelihood point and we're done. Okay? Very nice. There's only one problem, and a big one, which is that this requires inference. And we have to do this inference at each step. So this is going to be very expensive. Okay, so can we do something that's quicker? Yes, we can. So we can borrow this idea from the world of Markov random fields of pseudo-likelihood. And the idea of pseudo-likelihood is to be a measure that's like likelihood but doesn't require inference. And the pseudo-likelihood is just the product over all variables of the probability of the variable conditioned on the state of its neighbors in the data. Right? So all that we need to do is compute a conditional probability, and this is very easy. Right? And so this does not require any inference. It's a consistent estimator, so that's good. It's, this has been used a lot in fields like vision, spatial statistics, NLP, etc. It does have the problem that this is not quite the right thing to optimize. So if you have long inference chains at inference time, pseudo-likelihood didn't think about long inference chains, so the results might not be very good, right? So when this works, it's nice because it's very fast and reliable, but when it doesn't, you need something else. And so here's another thing that you can use, and that's discriminative learning, right? And these days, people tend to use discriminative learning over generative learning anyway because it's more accurate. So the idea here is that if you know in advance which variables are going to be query, let's call them y, and which variables are going to be evidence, let's call them x, then you can just maximize the conditional likelihood of y given x and not waste any effort modeling the joint distribution of the x's because you're going to know them at query time. Okay? So this is both more efficient and more likely to give you an accurate model because you will not be compromising prediction of y for the sake of better prediction of x. Okay? And now your gradient is still the same, except that now this is of course in terms of x and y, and we have fewer clicks to model and whatnot. Okay? And now there's another thing that we can do, which is what makes inference hard is that you usually have many isolated modes, right? But when you condition on things, those modes start to disappear. In fact, in the limit, they have to all disappear and leave only one. Okay? So what we can do is approximate this, which is essentially a sum over all possible states with just the values in the single most likely state. Okay? In the idea that hopefully there's a dominant peak and most of the probability mass is in that peak and nearby states, right? So instead of doing an exponential sum, I just need to find that peak, and then I use the counts on that peak as an approximation to my, overall counts, okay? In fact, this idea was originally proposed by Mike Collins for training hidden Markov models. And he called it the voted perceptron because it's a lot like the perceptron algorithm. And, of course, there the network is a linear chain, right? So these are my observations and these are my hidden variables, right? And the way voted perceptron works is you initialize the weights to 0, and then you just go into the cycle where you estimate the most likely y given x, in this case using the Viterbi algorithm, and then you do the difference between the counts in the data and the counts in the MAP solution, and that's your training signal. Multiply that by a learning rate, update your weights, and then you return the average of the weights. Okay, that's why it's called voted. This tends to give better results. So how can we generalize this to Markov logic? Well, the answer is actually very simple. All that we need to do is replace Viterbi by Max Walksat, right? Or by some other procedure for finding the MAP solution, right? By plugging this into here, right, this weighted satisfiability solver, or it could be, max product belief propagation or whatever, we now have something that applies to networks with arbitrary topology and, with arbitrary parameter tying, okay? And the algorithm is still pretty much the same, okay? And in addition to this, we have more recently developed, faster algorithms that use second-order techniques like scale conjugate gradient and Newton methods that, are often a lot faster than voted perceptron, okay? But the basic idea is still similar. Finally, structural learning. Well, structural learning is the problem of discovering what formulas hold in your data, right? And this is both a generalization of the problem of feature induction in Markov networks and the form of inductive logic programming, right? What inductive logic programming does is discover clauses that are true. There's a couple of important differences. The one is that here we want to induce arbitrary clauses, not just horn clauses. And our evaluation function now should be likelihood because we're building a probabilistic model. Okay? And in principle, any kind of ILP search algorithm could be used here, except that there's a big problem. Is that in order to evaluate a new candidate clause, a new candidate MLN, I need to learn weights for it. So now I need to learn weights for every single candidate that I'm going to try during the search. And that could be a really huge number, right? And, learning weights is not exactly instantaneous. Surprisingly, though, if you do a couple of very simple things, it actually turns out not to be the bottleneck. And the simple things that you can do are, first of all, when I modify a clause and relearn the weights, I don't start from scratch. I start from the current weights. right? Because chances are most of weights aren't going to change, and even ones that change aren't going to change much. Okay? And the other thing that I can do is have looser convergence thresholds, because I just want to figure out who's the winner, not exactly what the weights should be. At the end of each selection step, maybe I can do the exact weight learning. Okay? And things like LBFGS are extremely fast when you start close to the optimum. So what happens is that we often converge in just 2 or 3 iterations. Interestingly, the bottleneck turns out to be counting clause groundings, which is actually an NP-complete problem in itself, unfortunately. Now, when we were doing this for weight learning, we just had to do it once, and that wasn't too bad. Now, again, we have to do it every time we introduce a new clause. But again, there's a bunch of things that we can do here that speed things up, including caching and various kinds of subsampling that make things much, much faster, right? If a clause has 1 billion groundings, I don't need to go check whether each one of those is true. I can just subsample 1,000 and see what fraction is true and extrapolate that to the whole. And with that, structural learning in Markov logic becomes about as efficient as other kinds of ILP, which means it's not blindingly fast, but it's something that you can do in practice. And now you have the usual choices for initial state and operators and evaluation functions and various search algorithms and whatnot. Okay, you can do top-down search, you can do bottom-up search, you can do various combinations, etc.
Will this learn the kind of predicates that your data indicates are likely to be useful?
Yeah.
If you have a data set of people and their health states, will it learn that cancer is a useful thing to talk about?
For example, it will learn that smoking is useful in predicting whether you're going to get cancer or not. Yeah, that's exactly. Or it might, for example, it might learn that whether your friends smoke is predictive of whether you smoke or not.
Yeah.
Right. So
Have you been told about friendship and cancer in advance?
No. So there's another thing that you might want to do, which is predicate invention, where you discover the predicates. And again, this in some ways the most interesting problem. Something that we've worked on and others have worked on. I'm not covering it here, but I'd be more than happy to talk. This is actually where most of our recent work has been, because that really is the bigger challenge. So yeah. And it's a hard problem, but we've made some good progress in it. It's also another, the probabilistic equivalent of this is discovering hidden variables or latent variables. Right, so predicate invention and latent variables are really 2 sides of the same coin. And so what we're doing right now is basically, it combines those aspects. So let me briefly mention the software that this is implemented in. It's called Alchemy, and it's available at this URL that I will put up again at the end. And it has all the algorithms that I've talked about, and you can, encode your knowledge, your assumptions in first-order logic. This is usually something that you can do very quickly, and it's very easy to learn. And because, hey, if you know logic, you already know Markov logic at some level. And then it has a bunch of, nice programming language features like, you can link in external functions, and you can, define types, and you have, you can comment, the usual things. And very much, once we started using Markov logic, we realized that it really is best thought of as a kind of programming language in the same way that Prolog is a declarative programming language, except that it has some interesting new features. So I think it's interesting to sort of like compare Alchemy with what's available on both just the symbolic side and on the statistical side. Okay? So if you compare Alchemy with Prolog, in Prolog, your representation is horn clauses. In Alchemy, it's arbitrary first-order formulas. In Prolog, your inference engine is theorem proving. In Alchemy, we have a bunch of them, one of which is lifted BP, also satisfiability testing, weighted maxset, and things like that. But of course, the big difference is that in Alchemy, you have learning and uncertainty handling right out of the box, whereas in Prolog, you have to somehow add them after, and that's where your hard work begins. You can also contrast Alchemy with something like Bugs, right, which is probably the most popular package for graphical models out there. This is short for Bayesian inference using Gibbs sampling. So Bugs uses Bayes nets, we use Markov nets. And in fact, our representation is more general in the sense that basically Markov logic allows you to encode arbitrary log linear models. And Bayesian networks are only a subset of all the possible log linear models. In Bugs, your inference is Gibbs sampling, which is excruciatingly slow for a lot of models, whereas in Alchemy we have some much faster things available. In Bugs, you can only learn parameters. In Alchemy, you can also learn structure. But of course, the most important thing is that Alchemy is relational. In Alchemy, you can talk about relations between objects, non-IID data, etc. very easily. In Bugs, this is either impossible to do or very hard, depending on exactly what you're trying to model. Okay, so Alchemy, in some sense, it combines a lot of the best features of both of these. But the most important thing, of course, is that in Alchemy, you can basically have the logic and the probability and not even think about the distinction between the two anymore. Okay. and just have both capabilities at your disposal. Now, of course, both Prolog and Bugs are much more mature systems than Alchemy is, right? So they have a lot more bells and whistles and so forth than Alchemy does at this point. But for many things that you might want to do, Alchemy is already a better starting point than either of these. So as an illustration of that, let me, just to finalize, talk a little bit about applications. So as I mentioned, Markov logic is only a few years old, but it's actually been applied to a remarkable number of things by us and various other people. Here's a partial list of them. Information extraction is one, inter-resolution is another, link prediction, other natural language processing tasks, like Sebastian, for example, has done a lot of applications of Markov logic to things like semantic role labeling and inter-resolution and so forth, and won some competitions while at it. Web mining, computational biology, social networks, robot mapping, active recognition. Some of you might be familiar with Psych, the world's largest knowledge base. The folks at Psychor are turning parts of Psych into MLNs, so they can do probabilistic reasoning with them. Also, Kalo, the largest project in DARPA history, it used Markov logic for its core inference engine. And again, this was very successful there, and so on. So let me just pick one particular application, because I think there's nothing like seeing a concrete application to see, what the power of something like Markov logic is. So information extraction, a very important problem and, very widely studied these days, is the problem of going to text and extracting a database from the text that you can then issue queries to. And one popular example of that is citation databases like CiteSeer and Google Scholar. So the goal is go to the citation lists at the end of papers and extract out, the papers, right, to have a citation database. And there's basically two parts to this. The first one is segmentation, where I want to detect that IIIO6 is a venue field, and so is Proceedings of the 21st National Conference on Artificial Intelligence and so forth. Okay? The second step is inter-resolution. I need to figure out that IIIO6 and the Proceedings of the 21st National Conference on Artificial Intelligence actually represent exactly the same thing, right? And this can be very hard because, these two strings look completely different, right? And once I've matched the fields, I also want to match the citations as a whole. Like, I want to identify that these two are actually the same paper and these two are the same paper, right? Otherwise, I will get duplicate records when, my queries will return garbage, and any modeling that I try to do on top of this will also be broken. Okay? So the state of the art in inter-resolution today is to use something like an HMM or a CRF to do the segmentation by basically assigning each token to a field. Author, 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 title, 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 venue. And then the inter-resolution is done by taking a classifier, typically logistic regression or naive Bayes, applying it to every pair of fields or citations and predicting whether they're the same or not. And then you need to apply transitive closure, which can be done in a number of ways, usually a very heuristic ones, right? If I've decided that A and B are the same and B and C are the same, well, now I need to decide that A and C are the same as well. Okay? So if you were to go and, implement your own information extraction system using Java or C++ or something today, it would probably take you, on the order of weeks to do that, and it would probably run into tens of thousands of lines of code. In Alchemy, you can do this with just 7 formulas. So you can write 7 formulas in Alchemy that fit on a slide that implement a complete information extraction system for you. Okay? In fact, if you don't believe me, you can go and download this from the Alchemy site and do it yourself and try it out. In fact, I've given talks where people do that while I'm giving the talk and download it and come to me at the end with questions about what their system is doing. So how do we do this? Briefly. So an MLN file in Alchemy has 3 parts. The first one is type declarations, the second one is predicate declarations, and the third one is the formulas themselves. And the type declarations, in fact, are optional because the types can just be inferred from the data. Okay? So we almost never do type declarations, but for clarity, I'm going to do them here. So we're going to have 4 types here. The first one is token, right? This is all the words that appear in the data. The second one is field, which in this case is author, title, and venue, say, but it could be other things. It could be cities, it could be, companies, etc. And now I have, all my citations, and I also have an index to run over positions in a citation. Okay? So those are the types. Now the predicates. This predicate is going to be my evidence. It says that this token appears in this position in this citation. Okay, so the token singular appears in position 1 of citation 1. Okay? And now my query predicates are going to be these three. In field does the segmentation. It says that this position in this citation belongs to this field. So for example, the first position of citation 1 belongs to field author. Okay? And then these two do the anti-resolution, right? Same field means that this, for example, the author field in citations 1 and 2 are the same person. Okay? And same citation just means that the two citations are the same. Okay? So with these predicates, here's the MLN. It has 7 formulas as advertised, and they're pretty short. The first 3 formulas are basically implementing an HMM, or actually CRF, because we train this discriminatively, but either way. And the last 4, as we shall see, are doing the anti-resolution. So how are these formulas implementing an HMM? Well, it's quite simple. So this formula is saying that having a token in some position implies that that field is in that position. And all the open variables here are implicitly universally quantified, as in prologue. And we have this notation plus that basically allows this formula to be a summary for all the instances of this formula that you get by replacing this with all the tokens and with all the fields. Okay? So when we learn the weights for this formula, we're basically learning a matrix of token by field. And this is exactly the observation matrix of the HMM. Okay? And now the next one, not surprisingly, is going to be the transition model of the HMM. And what the transition model is capturing is the correlation between the fields of successive tokens. Okay? And this rule actually here is actually not even necessary, and let me jump over it. It's just to make things, better in some ways. So now the anti-resolution, the first rule that does a lot of the work is this rule that says if two fields have the same tokens, then they're the same field. Right? So the more tokens two fields have in common, the more likely they are to be the same. But of course, some tokens are more informative than others. And again, what we're going to have here is a weight for this formula for each token field pair. Right? So some tokens might be very indicative of some fields, in which case that instance of the rule will have a high weight. Okay? So you can look at this as a logistic regression where this is the predicted variable, and we just constructed these features for the regression. Right? So we're doing logistic regression where the features are defined by Markov logic, or by logic. Right? You can also look at this as just, it's a similarity comparison. Right? I'm comparing fields, and the more similar ones are more likely to be the same. Okay? So now I have a little rule that does a lot of work, which is a rule that says that if the fields are the same, then the citations are the same. Okay? Now, and vice versa. Notice this is an equivalence. Certainly if the citations are the same, right, necessarily the fields have to be the same. Right? But if the titles are the same, this is actually evidence that the citations are the same. Even if the authors are the same, this is weak evidence, right? So again, as logical statements saying that the same authors means that the authors are the same implies that the citations are the same is broken. But in Markov logic, this is just capturing a correlation. So same title would probably have a higher weight than same venue, and than same author, and same author a higher weight than same venue. Okay. And notice that this also does something important, which is if I figure out that, for example, those two citations that I have from AAAI were the same because the authors and the titles were the same, right? Now, since the citations are the same, the venues have to be the same. So at this point, I've inferred that AAAI and the National Conference on Artificial Intelligence are the same thing. So I've actually done something that you would think would require domain knowledge, but I've been able to indirectly figure that out just from the data. And even better, now this becomes available to match for the citations. Now that I figured that AAAI and the National Conference blah blah are the same, I can use this to match other things, right? So this rule is very short, but it actually does a lot for us. And then these two rules just implement transitive closure. And the beauty of it is that these rules, this is just the statement of the logical axiom of transitivity. Right? The only thing that we did here was add the axiom, if C is the same as C prime and C prime is the same as C prime prime, this C is the same as C prime prime. And you throw that in, and the system does transitive closure. A few years ago, there was a widely cited paper by McCallum and Wellner at NIPS, where what they did was to add transitivity to a CRF. And the paper was a tour de force because they had to design new inference algorithms, new learning algorithms. They had to basically do everything from scratch to make it work, to add transitive closure. In our case, adding transitive closure is just one more formula that you write. Okay? Of course, it increases the complexity of the inference, but fundamentally, as a user, you don't have to do anything different. Now, this, as an inter-resolution model, is actually a pretty good one. This, as a segmentation model, is not so great. And the reason it's not so great is that it's not very good at deciding exactly where the boundaries of the fields are. And people in information extraction know this, and what they usually do is that they write rules to basically predict where the boundaries are. Okay? But those are sort of like the rule-based approaches to information extraction, where CRFs and HMMs are more the statistical-based approach, right? Another question is, can we combine the two? Actually, we can combine them very easily just by taking, here's a simple example of how you can do that. In citation matching, there's a very good predictor of where a field ends. That's the period, right? Most fields are separated by periods. So all I need to do is modify this rule by saying, well, actually consecutive tokens only want to be in the same field as long as one of them is not a period, right? So the period stops the propagation of fields being the same, okay? And here's some experimental results from this on the core database. This is a standard thing that's used for these purposes. Here in green is the model without this change that I just made, right? So this is precision recall, you want to be up there, right? So this is just the logistic regression model, no sequential model. This is when you add the sequence correlation, right? And now when you add that, when you do that one modification that I just showed, suddenly you get up there. And now if you do the same thing for the comma, which often is a field separated but a weaker one, you get even better results. Okay? So refining your MLN to take more information into account is usually quite easy. You just change your rules or add new rules. And here are some more results. So okay, let me just briefly conclude now. If you look at other areas of computer science, there's a remarkably consistent pattern as to when the speed of progress picks up. And this is when people define what you might call an interface layer that separates the infrastructure from the applications. For example, in the case of the internet, of networking, the interface layer is the internet. And the infrastructure is things like protocols and routers, and the applications are things like the web and email and whatnot. And the power of this is that once you have this layer, the people doing applications above it don't need to worry about what's below. And likewise, the people who work on what's below don't need to worry about what's above. They just implementing this language. Okay? So the n-squared problem of every application communicating with every piece of infrastructure becomes an O of n problem. Right? And again, in pretty much every field you see this case. In databases, the interface layer is the relational model. Right? In programming languages, it's high-level languages. In VLSI, it's VLSI modules. In architecture, operating systems, for example, it's virtual machines. Right? In microprocessors are an interface layer. Right? In HCI, it's the graphical user interface. Right? So now we might ask ourselves, well, what is the interface layer for AI? Right? And in the early days of AI, some people would have said, well, it's first order logic, right? And then they would build like these expert system shells and whatnot. The problem though is that first order logic by itself doesn't have everything that you need to have a good interface layer for AI, so it hasn't really taken off in that way. In particular, it can't handle uncertainty. Right? On the other hand, some people would say that graphical models in some sense are like this, layer where you can describe all probabilistic models using graphical models and then, develop inference algorithms for them and so forth. But again, graphical models per se don't have everything that you need in an interface layer for AI. In particular, they work with a very impoverished representation of the world, just a vector of variables. They can't talk about relations and objects and things like that. However, if we combine the two in something like Markov logic or a similar language, now potentially you do have a viable interface layer for AI. Okay? Because now you have combined in one language everything that you need. And now, if you work, for example, in learning, right, you can develop learning algorithms as long as they use these APIs, they become available for all the applications, and they will work with the other pieces without you having to worry about it. Right? So if you like, inference, right, maybe you have a better stat solver, well, that can then work with the learning even though you yourself don't have to know anything about the learning. And if you're on the application side, right, you don't have, like for example in NLP today, people build these NLP systems that basically have everything implemented in them and they spend their entire time maintaining them instead of doing NLP research. Right? With something like this, then you at least potentially are able to focus on what you care about, which is the application. And our goal with Alchemy is, of course, to support such an interface layer So as someone on the application side, you can use alchemy and produce MLNs. As somebody on the infrastructure side, you can produce algorithms, and as long as you use the alchemy APIs, they then become available to the people doing applications. And ideally, and we're starting to see this, if when you do an application, you take your Markov logic network and you make it available, then others, right, can start from your Markov logic network and pick and choose the ones that they need, and then build on top of that. And hopefully in this way we can actually make faster progress towards human level AI or something approaching it. Thank you.
This production is copyright the University of Edinburgh.